All right, well, welcome back. So in this section, we're actually going to be taking a slight detour from our study of elliptic curve cryptography, and we're actually going to be showing a pretty fun application of elliptic curves in the world of factorization. So to set the stage as to why factorization is so neat, let's just quickly remind everybody of the world of the RSA public key crypto system. So down in front of you can see my terribly drawn images of Alice and Bob. So the way that I've set this up is I've created this channel so everybody can actually send messages to Alice. So if I wanted to switch it around, I just change the roles of Alice and Bob. So over on the left-hand side, we have Alice in her festive little Western wear, and she has to first create this public key that she's going to release out into the world. So there are two components to this public key. There's going to be this modulus n, which is actually created by grabbing two of her favorite prime numbers that are genuinely viewed to be fairly large, and she's going to be multiplying those two things together and releasing the product n out into the world. Along with this public modulus n, she's going to be creating this little encryption exponent e. And that little e is chosen such that it is actually relatively prime to the product p minus 1, q minus 1. That is, if you compute the GCD between those two objects, it's going to fire off a 1. So those two things together, so the n value and the e value, get published out into the entire world. So everybody knows what those two things happen to be. In the background, then, she's got to do one extra little bit of arithmetic to create her very secret little decoder, or her decryption exponent, d. And this is where all the security is actually embedded, is that her creation of d is actually dependent upon her knowing the factorization of what n happens to be. So this little d is actually created by taking that little encryption exponent e and finding the inverse of that thing with respect to p minus 1, q minus 1. So that's the kicker in all of this, is that she knows the factorization of n, so she can easily compute p minus 1 and q minus 1. So on the other side, we got this dude, Bob, who wants to send some messages off to Alice. So he's going to take his secret little message, whatever it happens to be. That message is going to be viewed as some little m modulo this modulus n. And he's simply going to encrypt this thing by taking that little m, raising it to the eth exponent, so this encryption exponent, and then taking that result and reducing it mod n. So he easily can compute this little ciphertext, which is what we have over there, and he sends that thing off to Alice. So Alice receives this little ciphertext, and she can easily decrypt that thing because she knows what her secret little decoder d happens to be. So all she's got to do is take the little c, raise it to the dth exponent, reduce that thing mod n, and it's going to return what Bob's secret little message happens to be. So in the middle of all this, we know is going to be our favorite little adversary, Eve, hanging out. And she can see what the n happens to be. She knows what the encryption exponent e happens to be. And she actually can see what message Bob actually sent, the c. The only thing she doesn't know is she does not know what this decryption exponent d happens to be. So if she can easily factor that little n, so that is if she can identify what the p and the q happen to be, well then she basically becomes Alice. She knows what p and q are, so she can easily compute what the inverse of e with respect to p minus 1, q minus 1 happens to be. So then she knows what her decryption exponent is going to be, and she can record or read any message that Bob's going to be sending her. So everything in this is based on this assumption that factorization is really, really hard. So we know that there's a plethora of factorization algorithms out there. We actually studied some of these last semester. And I'm just going to kind of remind you of a couple of the key ones and show you where today's chat essentially is going to fit into the mix. So factorization, you can start with just a classic brute force approach. The idea is you just take your number and you begin just trying to divide by various primes up to a certain bound, and you can maybe record a factorization. Brute force works great if one of the primes, p or q, happen to be small. So if you think about taking your prime to be 7, well, you don't got to go very far to find that factor of 7. We also had a couple other ones. So we have ones like Fermat's factorization algorithm. So that one is actually really good if the primes p and q happen to be close to one another. We then had Pollard's p minus 1 factorization algorithm. And on the next slide, I'm just going to really quickly go over that one again because there are some similarities of this one with this Lenstra's elliptic curve factorization algorithm. So that one's really good if p minus 1 happens to have a bunch of small factors. Then we got the elliptic curve factorization algorithm, which is actually the bit that we're going to be talking about today. And we have a few other fancier ones, so the quadratic sieve as well as the number field sieve. Those are actually some sub-exponential factorization algorithms. And the one that we're going to chat about today is actually another sub-exponential factorization algorithm that is really pretty easy to implement. It does require some arithmetic in these elliptic curves, so it's a little bit clunkier to work with, but overall it's very easy to actually implement. I have a few different versions of it running in Sage, so I'll put you to work trying to do some factorizations and see some kind of fun things happen. So to remind you of some of the other factorization algorithms, I have just a really quick outline of Pollard's P-1 factorization algorithm. And the big kicker on this is that there are some similarities between this and the elliptic curve factorization algorithm we're going to be looking at. The idea is that this one has a whole bunch of operations happening until a certain stage of something breaking. And that's what's going to happen today as well, is that we're going to be doing a whole bunch of additions on points in an elliptic curve until we can't do that anymore. The moment that something breaks, we're actually going to be able to record what one of the factors ends up being, which is exactly what ends up happening in this P-1 factorization algorithm, is that we begin by taking some base, which we usually choose to be at 2, and then we begin raising that thing to larger and larger exponents. In particular, we're going to be looking at taking, let's say, 2 and trying to compute 2 to some k factorial exponent. And that's really pretty easy to do. All you got to do is take your previous answer and then just raise it to the next exponent. So we can very quickly generate this massive list of 2 to some huge k factorial. So this is 2 to the k factorial. So you keep on creating this little list as you go. And then along the way, you're going to be computing this little GCD argument. So you're going to be taking this number that we just compute, you subtract 1 from it, giving you this object, and then you compare that number with the number n that you're trying to factor. Most of the time, it's going to return a 1 up until some point. And once you get to that point, you're going to see some magic little d emerge, which is actually one of the factors for that n value that you're given. So it's pretty slick. It's not that many steps in terms of the overall factorization. You start with this little base a. Usually we choose this a to be 2, but you don't have to choose a 2. And you begin looping through just by taking the previous answer and raising it to the next exponent. It's this idea that if I want to compute 2 to the 43rd factorial, well, you can take 2 to the 42nd factorial and then raise that to the 43rd. And using a blue pen on a blue border is terrible to do, but that's actually a 43 there. It's just really, really hard to see. So that's what's happening in this little bit. You're just going to keep on taking that and run it to compute these larger and larger little exponents. And then at some point in time, you may actually see this non-trivial d actually emerge. The moment that that actually happens, we actually do have a proper factor of this little number n. And you can easily record the other one just by dividing by whatever thing you happen to find. So here we found out one of the factors of this n value ends up being 5591. So to compute the other one, all you got to do is you got to take that number n and divide it by 5591, and you easily record what the other factor, the q, ends up being. So there's some interesting bits about how long this process has to run. So this one runs up until a k value of 43. So we had to compute 2 to the 43 factorial and then compare that minus 1 against the n to see that little value p emerge. And that comes from this idea that if you look at that prime that we ended up seeing, if you compute p minus 1, it is recorded as 5590. Which actually factors down into 2 times 5 times 13 times 43. So 43 is the largest divisor that lives in p minus 1. So p minus 1 is not made of very crazy stuff. So we knew that p is prime. P minus 1 is for sure going to be some even bit, and ideally it's going to have some other stuff as well. And you can see that the other stuff is a 5 and a 13 and a 43. So this process needed to go all the way down until level 43 to actually find the factor. So in terms of this big scheme of all of these factorization algorithms, this P-1 factorization algorithm is really good if P-1 only contains small factors. So if P-1 is a whole bunch of 2s and a whole bunch of 3s and a whole bunch of 5s, that thing's going to terminate almost immediately. The elliptic curve factorization algorithm that we're going to look at today is going to have some similarities to that, is that we're going to be running this thing until something breaks. The point in time that it breaks is going to give us some information about what the little factors are all about, and we get a really fast, or at least a decently fast factorization algorithm that we can kind of pull in some of these components of elliptic curves and really kind of see a fun application. So I really like this factorization algorithm because it's kind of cute. It takes something that you're not really expecting to bring about factorization, and then all of a sudden it's right back full circle.